Today we're going to take a look at the concept of inverse functions. And it's a really good idea right now to remind ourselves a little bit of some of the vocabulary, some key terms in regards to functions first. One of the things that we're going to find out is inverse functions have a lot to do with reflections and gratuitous kitty gifts. So we remind ourselves that a relation is any connection between two variables. So when you have any set of ordered pairs, that's a relation. Okay? A specific type of a relation is a function, and that's a relation where the independent variable, which is the x variable, the one that's plotted on the horizontal axis, is always different or unique. It's never paired with more than one y value. When we look at a function on a graph, it will always pass the vertical line test. So in other words, if we were to take a vertical line such as a pen or a pencil and move it from left to right vertically across the graph, it will never make contact with the graph in more than one place at the same time. If it only touches it at one place at a time, that tells us that yes, it is a function. So now we want to think about the idea of an inverse relation. So to make an inverse relation, we change the position of the two variables. So for an ordered pair, we're just going to change the order of the coordinates. The x becomes the y becomes the x. In an algebra equation, we're going to do the same. We're going to take the x and put it in place of the y, and the y goes where the x was. When we graph, we're actually going to reflect the graph across the line y equals x, which remember, that's a 45-degree angle through the origin. And that, too, will switch the x and y values in our graph. So let's look at some examples. If we have the ordered pairs 1, 2, 2, 2, and 3, 2, this, by the way, is a horizontal line that goes through the point y equals 2, the inverse of that function is going to be 2, 1, 2, 2, and 2, 3. So now we have a horizontal line that goes through x equals 2, which recall is not a function. It is a relation, however. To take the inverse relation when we're given the function, for instance, y equals 2x plus 3, it's solved for y, so this is very easy to change out the x and the y. The x goes where the y was, and the y takes the place of the x. So now we have x equals 2y plus 3. And in the case of a situation where we've got a graph, so for instance, here's the graph y equals x squared. Okay? So if we traded out the x and the y in this case, we would have this graph, which it's pretty easy to see as a reflection across the line y equals x. A couple more terms for us to think about. So let's talk now about an inverse relation that happens to be a function. If the inverse relation is also a function, we refer to that as an inverse function. So the y values from the original relation, which are now the x values, are also different or unique, only used once. Our inverse function will pass a horizontal line test, so now we could go ahead and move a horizontal line from top to bottom past this graph, and it will only touch this graph in one place. So the inverse of the original now is a function. If that's the case, we say that this is 1-to-1. A relation is 1-to-1 if both the original relation and the inverse relation are functions. So all the x values and all the y values are unique. And that original relation will pass both a vertical and a horizontal line test. So let's look at a couple of examples. We're given the relation 2, 3, 3, 2, 4, 1, 5, 0. So our first question, is this relation a function? Is there ever a case where the same x is paired with more than one y? And we can see that that's not the case. So now let's find the inverse. So I'm going to trade places. The x becomes the y becomes the x. So 3, 2 replaces 2, 3. 3, 2 becomes 2, 3. 4, 1 becomes 1, 4. 5, 0 becomes 0, 5. Is this a function? Again, never a time when the same x is paired with more than one y, so yes, this is a function. So this would be 1 to 1. Let's take a look at another. Is this original a function? Negative 2, 1, 2, 1, 3, 1, and 0, 1. So remember, this is going to be a horizontal line that passes through the point y equals 1. It is a function. Let's now find the inverse. The y is going to take the place of the x. So 1, negative 2. 1, 2. 1, 3. 1, 0. It's pretty clear to see now that we have the same x repeated paired with 4 different y's. So not a function. Go ahead and pause the video, and you try and do number 3 on your own. Now you can check your work. Is this a function? 0, negative 1, negative 2, negative 3. I never have the same x paired with more than one y. So yes, this is a function. Now let's find its inverse. 1, 0. 2, negative 1. 3, negative 2. 4, negative 3. Never a case where the same x is paired with more than one y. So yes, it is a function. Let's move on ahead now. Once we know that we can find an inverse function, our next question is, can we write an equation of the inverse of a function? We use some interesting notation here. We say that this is f inverse of x. F written like it's to the negative 1 power. We say f inverse of x, the inverse function of x. So we trade out the f of x for y. So we're going to write this the way that you learned to write an equation in Algebra 1. Then we're going to switch out the x and the y values, solve it for y, and then once we have y equals an expression, we replace the y with f inverse of x. So let's walk through the process. Y equals negative 2x plus 1. Okay, we're going to change the x and the y. X equals negative 2y plus 1. Now our job is to solve this new expression for y, trying to get y by itself on one side of the equal sign. So I'm going to subtract 1 on both sides. X minus 1 equals negative 2y. Divide by negative 2. So negative 2 divided by negative 2, that's just 1, so I have 1y. I have negative 1/2 x plus 1/2. So the x divided by negative 2 and the negative 1 divided by negative 2. So my last move now is to replace the y with f inverse of x. So negative 1/2 x plus 1/2 would be my inverse function. You can pause the video and try the next example on your own. Now let's check your work. We're going to trade places the x and the y. Now let's solve this one for y. Add 2, add 2. So to divide by 3/2, I'm going to multiply both sides by 2/3. So 2/3 times 3/2, that's 6/6, that's 1. So I have y by itself on one side of the equal sign. 2/3 x, 2 times 2/3 is 4/3. And now I can replace my y with f inverse of x. What about a more challenging example? So y equals the radical x plus 3. And you trade places with the x and the y. And now solve for y. Now remember, I can't just go subtracting 3 on both sides because this is underneath the radical sign. So I'm going to square both sides. X squared equals y plus 3. So now subtracting 3 on both sides. X squared minus 3 equals y. We're going to replace the y with f inverse of x. Similarly, with a bit more challenging one. Divide both sides by 3. And I can actually leave this in this form. So f inverse of x equals x squared plus 2 over 3. Finally, thinking about graphing the function and then graphing its inverse. So we make a table of values for the original function f of x and plot the points, connect the points to make the graph. Now, in a second table, we switch out the x and the y to make a table of values for that f of x. Now we can graph our inverse graph. So let's look at f of x equals 3x minus 1. So let's start plugging in our values to make our table. Negative 3 times 3 is negative 9, minus 1 is negative 10. Negative 2 times 3 is negative 6, minus 1 is negative 7. Negative 1 times 3, negative 3, minus 1 will be negative 4. When 0 is in there, it's negative 1. 1 times 3 is 3, minus 1 equals 2. 2 times 3 is 6, minus 1 would be 5. And then when 3 is in there, this is 8. So negative 3, 10. Negative 2, 7. Oops, those are negative. Negative 1, negative 4. 0, negative 1. 1, 2. 2, 5. 3, 8. So that is our line, y equals 3x minus 1. Now, we're going to switch our x and y values. So negative 10, negative 3. Negative 7, negative 2. Negative 4, negative 1. And let's see what happens. So I go to negative 10, negative 3. Negative 7, negative 2, negative 4, negative 1, negative 1, 0, 2, 1, 5, 2, and 8, 3. So our big question now is this line a reflection of this one over this imaginary line, y equals x? If it is, we'll be able to see that these 2 points are equidistant away from y equals x. And yes, that's correct.